got to wonder, why is there such a lot of hype? And it's basically very simple. The growth has been incredible. Unprecedented worldwide growth. And there's no sign of it slowing down. If anything, it's accelerating. And you look at the numbers for Sweden. I mean, Sweden was incredible last year. Last year we spent more in Sweden on high-end additive manufacturing than in the last 15 years combined. Now, possibly the reason for that is Sweden was a little bit behind the rest of the world, so we're catching up and we're having to do it quickly. But that growth is incredible, and it is very, very exciting. So the hype is deserved. There is a lot of growth and a lot of opportunities, but it is interesting to start looking a little bit at why. So to me, it's a bit of a reality check. Can additive manufacturing be used today for production? For prototyping, absolutely. It's been used for almost 30 years extensively for prototyping. Very few companies today are not using 3D printing for prototyping. But for manufacturing, for some applications, absolutely, as it is, as the parts come off the machine today, it is usable. But very few applications today straight off the machine. Most of them require a lot of post-processing. We'll talk about that. So you might be wondering why I've got pictures of sandcasting down the bottom, because it's a 3,000-year-old process, probably one of the oldest manufacturing processes known to man. And probably the reason is, in my opinion, today additive manufacturing is very much the same as sandcasting in terms of the quality of the parts that come off the machine. Both metal and plastic. The surface finish of the parts, the metallurgicals or the polymer properties of the parts are similar to what you would get off of sandcasting. Now, if you hip them, if you post-process them, if you heat treat them, you can get up to forge strength. If you machine them, you can get mirror surface finishes on them. But straight off the machine, if you think of a part coming off a 3D printer in a similar way that you would think of a sandcasting, you will not be disappointed. And that's when you can start to exploit the potential of what additive manufacturing can do. And in particular, one of the most important take-home messages for today, I think, is that I don't think additive manufacturing will ever replace conventional manufacturing. I think the factory of the future will have several additive manufacturing systems, polymer and metal, together with CNC machines, injection molding machines, die casting, all the processes together. And I will give some examples of that. So to me, one of the most important things, if you want to adopt additive manufacturing, is to use it for the right reasons. To use it for the advantages that it gives you over conventional. And Joachim talked about some of those. The best known of those advantages, of course, is complexity for free. The more complex a part is, the better suited it is to additive manufacturing. So this is an example from American Standard that do luxury tapware for your kitchen. And you look at that one on the right and you try to think, how does the water get from the bottom to the top? It's because with additive manufacturing, you can print these incredible twisting pipes that you couldn't make any other way. Beautiful example of design using complexity for free. Now, just a note on these, 12,000 US dollars, so 120,000 crowns. So think art for your kitchen. But additive manufacturing, as it is today, is very much on the low volume, high value side. So for products like this, beautiful, beautiful example. Artists and designers love additive manufacturing for this, and they're really pushing the limits of that complexity for free. But maybe on the engineering side, the complexity for free gets more useful. And this is where we talk about topology optimization. So this is the little titanium 3D printed bottle opener that I've got on my keychain, sort of the ultimate accessory. And with luck, I think they may be printing some of these in the machine that you're going to see later today. Maybe. So topology optimization uses mathematics to remove the material that is not serving any structural purpose. So if you look at the chairs you're sitting on, there's probably 30 to 60% of the material in those chairs that structurally is doing nothing useful. So why not get rid of it and make the chairs lighter? And that's what topology optimization is all about. So this particular bottle opener, if you were going to make it the old-fashioned way, you would start with a block of, in this case, aluminium. So the block of aluminium would weigh about 10 grams. You'd bolt it onto your CNC machine, machine away to get to the center product, and that would be your finished product. It would weigh around 4 grams. You might be able to shave a little bit more off by using very fine cutters, but you'd still be stuck around 3 to 4 grams. Compare that to less than a gram for the topology optimized one. That's a 90% weight saving. Now, this is an extreme case. Typically, you will not get 90% weight savings, but 30 to 60%, relatively easy to achieve. And of course, this is why the aeronautics industry is going crazy over this. Joachim talked about the fly-to-buy ratio. Every kilo you save on an airplane is thousands of dollars of fuel you save. Formula One race cars, If you save a few grams, that could be the difference between winning and losing a race. And we're seeing this applied more and more in applications where you need lighter weight products. The next example is one that we did just at the end of last year with Tetra Pak. So an example of complexity for free. This is a really boring part. It's an induction sealer. So it's a stainless steel bar, pretty boring as a component, and it's got a copper induction coil in the middle with a bit of plastic surrounding it. This is what they use to seal milk cartons. And the little round bit you see in the middle is where the plastic screw cap on your milk carton goes. Now with sealing machines, the faster you can cool the sealer down after it's sealed the cardboard, the faster you can run the machine. So how quickly you can cool down the part is essential. And in this case, you can see on the bottom when those red lines indicate the cooling channels. And the way they make those today, they drill a hole, drill a long hole to join them, block off one little part of the hole, then they can run water or oil through it to cool it. It's better than nothing. It works. We redesigned it for them, and two things we did. The first thing is we emptied it out, hollowed it out, and put a lattice structure on the inside to keep the structural integrity, but we lost half the weight. So it went from 320 to 160 grams. Now, it may not be a big deal in this case, but if the part is lighter, the motors don't have to work as hard, less effort for the machine so you can run it faster. But the really big change, and now you can see the red line showing the cooling running from one end to the other, much more efficient cooling. Because with additive manufacturing, again, we can make much more complex channels than you could with regular manufacturing. And it starts off round at the bottom. As it goes around the bend, it goes into a triangular section, so you get a much wider area of cooling, much more efficient cooling. And that, you can see it on the right there, printed in 316 stainless. I think that's what the material was. And we cut one in two just so we could show Tetra Pak what the inside looked like. And they're currently testing this to see how much better it is, how much more efficient it is. So watch this space. There's a lot going on in this area of making more efficient parts this way. Next big advantage, mass customization. And what we mean by this is I want to make a product for everybody in this room, but every product is custom made to you, the user. With conventional manufacturing, every product has to be the same. Otherwise it gets too expensive. With additive, other than the design side, it doesn't make much of a difference. But what's interesting here is look at the quantities. The quantities are pretty serious manufacturing quantities. Hearing aids, over 60 million produced to date. It's about 96% of the inner ear hearing aids made with 3D printing today. We saw acetabular cups, the hip replacement, dental coated, 6.8 million a year. The really interesting one, which I think demonstrates the factory of the future, is at the top there, the dental aligners, Invisalign. So this is a new way of lining up your teeth. Instead of the old railroad tracks, they give you, it's almost like a little rugby mouth guard. You put it in your mouth, and every week or every 2 weeks you get a new one, and it gradually adjusts your teeth until they're straight. Now this is interesting as manufacturing, because we talk about a lot of products as 3D printed products, but really they're not. And again, I'll talk about guitars later. I talk about my guitars as 3D printed guitars. They're not 3D printed. They use every manufacturing product under the sun. And in the case of these dental aligners, it's a perfect example. What they do is they scan your teeth, build a digital model of your teeth, and print that. That's the only part they print. Every 2 weeks they'll adjust the model and print a new model. The rest of it is done using conventional manufacturing. So the mouth guard is actually made with thermoforming, so vacuum forming a sheet of material over the 3D printed model. Then a CNC machine around that to trim everything out with a 5-axis CNC machine. So their factory has got 50 SLA machines, 50 CNC machines, all in the same environment. Tumbling machines to smooth them out, packaging machines. So this really is a nice demonstration of the factory of the future where they're using additive manufacturing for the part that actually adds value. Printing the whole thing would not add value, so why do it that way? Another example that we did in Lund, this was just at the start of this year where Emily, the student who was doing this as a master's project, presented a thesis. This is for Lund Hospital and a company called Active Orthopedics. They make prosthetics. And on the right there you see Naya, a 2.5-year-old girl missing the bottom half of her arm, and with a low-cost scanner, a $300 iPad scanner that turns your iPad into a 3D scanner, we scanned the residual limb and made her a prosthetic that fits her perfectly. The old-fashioned way of doing that, she would have to spend an hour with her arm in plaster to get a mold of the arm. They would turn that into positive. They would then spend many hours sculpting. Artists and craftsmen would be working on this to get it into the right shape. In comparison, doing it the new way, the scan takes 10 to 15 seconds, very, very quick. It's an hour or two of manipulation of the data on the computer to get it right, print it in a few hours, and you're ready to go. Now this is a 2.5-year-old girl, so in, I don't know, 3 months, 6 months, she's going to need a new one and a new one as she grows. Really, really nice. So this is a 260% time saving. And they've now spun this out into a little commercial company, which is really, really nice it's a nice sort of Swedish success story. The other thing that's interesting is we knew the prosthetic was comfortable, because you can imagine a 2.5-year-old kid with something that's not comfortable, they'll just try to rip it straight off. And she was happily playing with it for hours, and she was quite proud of it. This was something cool that she could show off. And you can imagine in the future, you might have an app where she can drag Hello Kitty patterns onto it or customize it herself before printing it. In this case, the project was to do the recipe, and the real prosthetic is the one you see in the middle there. That's got the myoelectric implants to pick up muscle movements to control a bionic hand. But the one on the right was the passive prosthetic that she can wear when she's just running around the house. So again, mass customization you will hear much, much more of. The other big advantage from an engineering point of view, and this is related to complexity-free part consolidation. Taking a product that's made up of 50, 100, many, many simple parts, putting those simple parts together into a much more complex part. And this is a nice example from NASA, who did a rocket engine printed in 2 parts. And there's those 2 copper-looking parts that you see in the middle. On the outside, they look really boring. On the inside, believe me, they're not boring. They're very, very complex with pipes, tubes, baffles, to direct all the energy where you want. But imagine that. Think about that going from 115 to 2 components. Reliability, less assembly labor, less parts to keep on shelves in stock. All of the financial, the business issues that come to being able to simplify your product to less and less parts. So another example of part consolidation, this is one I was involved with about 3 years ago in New Zealand. This is a pitot tube. It's a little tube that sits underneath drones to measure airspeed. It's got 2 compartments in it, and the pressure difference in the 2 compartments tells you how fast the airplane is going. And we did this for the New Zealand Navy. So in New Zealand, the Navy runs all the drone programs, probably because we don't have an Air Force. And the way they've been making them until now, you see on the top left, 32 components brazed together. And they came to us and said, we've heard about additive manufacturing. We'd like to try it. We'd like to make this pitot tube using additive manufacturing. So we redesigned it for them, and we printed it out as a single component in nylon the first time to test, and amazingly it worked. Now there were some catches, a few things. In the center of it, there's a 1 millimeter inner diameter pipe. For those of you who have printed nylon powder before with laser sintering, removing the powder from inside the thin tube is a nightmare. It took us several hours just to clear out that little inner tube. And the other thing we didn't know is in New Zealand, when the drones land, they land on the beach. And this is underneath the drone, so the front of it gets filled up with sand. And every time they fly it, they have to shake the drone upside down to get out the sand. So the final one that's gone into production, you see down the bottom, is printed in titanium and has had a little screw-off cap that you can screw off to shake off the sand. And we've done a little cutaway on that one, so you can see that 1 millimeter inner diameter tube that leads to the front. Now again, 32 components down to 2 components. And again, reliability, ease of assembly, and so on. It just has an incredible advantage in that respect. So those are the, shall we say, engineering advantages, that complexity for free, the mass customization, the part consolidation. Now we get into the, call it the softer side of things, but from a business point of view, probably the more advantageous one. And this is being able to go to market. It's tool-free production. Typically, if you have an idea for a product, the tooling, the injection molding, the sheet metal forming, the extrusion, all of that tooling costs tens of thousands, 50,000, hundreds of thousands of dollars, millions of crowns to go into production. That often kills the idea before it even takes off. With additive manufacturing, you can go into production without that high initial cost and essentially reducing the risk of taking your idea to market. Doesn't mean your idea is a good one and should go to market, but it allows you to test it to see whether it is a good idea to go to market. So, a couple of examples of that. This was Max 4, the big cyclotron facility they're building in Lund. This is one of those super science things. I don't actually know what the machine is. That second image on the left, that big stainless steel chamber, I don't know what it is. It'll be some kind of a vacuum chamber where magic science happens. They needed lights to illuminate what's going on the inside. And you can see it on the right there. It's got LEDs that shine up the inside so you can see what's going on in the chamber. They came to us with their CAD files and said, can you print us one of these? We want to test it out. We printed it, next day gave it to them, they tested it, and it worked perfectly. They came to us the next day and said, we need 16 of these. Now that is the end of production. That is all they're ever going to need. Now imagine 16 of a product. How do you go into production with that? You're going to tool up for it? Probably not. Even CNC machining, which you could do, would be not particularly cost effective. So we've only got a baby machine in Lund, so we had to do it in 2 builds. So we did 1 build one night, 1 build the next night, and we did 16 of them for them, and that was the end of production. So again, the point here is not having to spend a lot of money on tooling to go into production. Another example of instant production. This is one we did for Atlas Copco earlier this year. So Atlas Copco can see that they need to get into additive manufacturing. They're not entirely sure yet why or what to use it for. They just know they need to be there to be ready for it when it does become applicable. So Seema, the lady who heads up innovation at Atlas Copco, called me up on a Friday and she said, I've got a meeting with the board next Friday and I need something to really impress them so they go, wow, 3D printing is cool. Can you build me a drone? And I said, don't be stupid doing a drone. No way, impossible. But she talked about it, she explained to me what she wanted and why she wanted it. So on the Friday, I went to Hobex and bought a drone to rip the electronics out of it, because there was no way we were going to be able to do the electronics in a week. Over the weekend, I catted up the files, printed them on the Monday, got them out of the machine on the Tuesday, assembled the drone, shipped it to her on the Wednesday, she received it on the Thursday, and was able to fly it at the board meeting on the Friday. This is it flying down the hall at Älmhult at the university. So the ability to get products to market very quickly to reduce those lead times is absolutely invaluable. And how much money that's worth, well, we don't know. We just know it's worth a lot to be able to go to market earlier and faster. Another example, this is one of my students in New Zealand, Jenna, who does a lot of mountain biking for Red Bull. So she travels around the world with her mountain bike, and when she travels, she has this big cardboard box, and it's not easy for her to get around the airport. She can't put the box on a trolley because then she can't get through the doors. So she has to basically carry this box around. So for her 3rd year design project, she said, I know, I have a great idea. I'll print out a little set of clip-on wheels that you can clip onto any box. And the wheels, of course, you can go to Biltema and buy some skateboard wheels for almost nothing. No point printing those, but the little clips that clip it on, they had to be sort of custom designed. She did those, printed them. She started to travel with these, and other athletes said, ooh, that's cool, can we buy some? So she sold 1 pair, she sold another pair, she sold another pair. When I left New Zealand 2.5 years ago, she sold somewhere between 70 and 80 pairs. Not a lot, not a business, but enough to test the idea to say this could be a business. And now she can decide, I'm going to sell 1 million of these, I'll injection mold them, invest some money, or this is high value, low volume, I'll keep making them with additive manufacturing and sell them that way. The point is she didn't have to go to the bank to say, please sir, can I have some money to test my idea? And that's one of the beauties of additive manufacturing, is being able to take products to market in the easiest possible way and at a very, very low risk. Next one is my own example. There was a story in 2011 called Print Me a Stradivarius, where somebody printed a violin. In my younger days, I used to play a lot of music, and I saw this story and I said, that is so cool, I've got to try it. So I tried printing out my first electric guitar. The first one is actually a spider version of the pink one you see in the top there. And the reason it's that shape is that's the biggest I could fit in the machine I had in New Zealand. I was amazed by how well it worked. It sounded good, it played great. So I started a little blog showing, just to show the rest of the world something cool that had been done with 3D printing. And the response from musicians was phenomenal. They were blown away and said, that is incredible, can we buy one? So same problem as Jenna. I scratched my head a bit and said, what do I do now? Sold one, sold another. I'm now building number 74 and 75 this side of Christmas. And possibly there's another 2 waiting to be ordered now. So about 12 of those are in my collection, the rest have been sold. So this really shows complexity for you. All of the designs are purposefully complex, because otherwise there'd be better ways of manufacturing than additive manufacturing. Every guitar is custom made for the user. And we'll look at the steampunk, the second one on the right there. But before we did, it made sense because I was building basses and guitars, it made sense to build the rest of the band. So I did a drum kit, keyboard, and a saxophone so we could have a full 3D printed band. Because you can. So, the one that's sticking out there, the steampunk one, just to show you again that complexity for free. Here's a little video of a clip of it in action. All the moving parts, but what really hurts the brain is the body with all those moving parts printed in one piece, assembled, ready to go. No assembly required. And that really sort of, you scratch your head saying, how is that possible? But this is one of the beauties of additive manufacturing. You can print moving parts. Now, from an engineering point of view, the tolerance in those moving parts is awful. You probably wouldn't be able to do it. But in this case, from a decorative point of view, more than good enough. So a nice example, again, of what you can do with additive manufacturing from that point of view. Now we get into the slightly less known part of additive manufacturing. Additive manufacturing and its effect on the supply chain, how it's going to change business in the future. So this is the supply chain before the Industrial Revolution, where if I, for example, if I wanted to make a chair, I made it myself. Possibly if I needed some nails, I'd go swap some eggs with a blacksmith, and that was the economy within the village. If my chair was really great, which I guarantee it would have been, I would sell it to you guys, the rest of the village, and the village on the other side of the hill, probably too far to deal with. So that is very much how the economy worked. Compare that to the economy of today. And conveniently, we're in Älmhult, the home of IKEA. So as the customer, I would drive to IKEA to buy my chair. They would get it shipped in from a warehouse. I have no idea where, but say Älmhult. They would get parts shipped in from Guangzhou in China, manufactured somewhere else. That supply chain is absolutely enormous. And it's expensive. Most consumer product, only about 10% of the cost of the product is the product. The other 90% is that supply chain. Cost of transport, of course, but also each one of these guys, 5%, 10% more adds to the cost. So imagine what would happen if additive manufacturing allows us to reduce that supply chain. So by that we mean go back to almost before the Industrial Revolution. Bring back manufacturing locally. Manufacture parts where they're needed, when they're needed. And that's sort of what we hope, we think additive manufacturing may bring to the future. It's going back to that chain where in each town there'll be a 3D printing center. When you need your chair, you'll walk up to them with a memory stick and say, I need my chair, go have a cup of coffee, come back and your chair is done. Now, of course, we're nowhere near there yet. Currently, most of the technologies are single material technologies. Most products are multiple material. But there's a big effort underway now in Sweden looking at spare parts. Can we make spare parts as we need them, when we need them, instead of keeping truckloads and boatloads full of spare parts? So, looking at spare parts, some frightening numbers. Automotive industry, $750 billion worth of spare parts doing nothing useful. Tetra Pak is, again, as an example, 800,000 unique spare parts sitting in shelves in Lund. They estimate 70 to 80% of those parts they will end up scrapping. They legally have to keep them for 20 years. 20% of the parts they send out all the time, the others almost never. Think of the value of that money sitting there doing nothing useful. Imagine being able to liberate that cash to do useful things. And that's, again, the potential that additive manufacturing has. But again, the technologies today are probably not good enough in terms of the surface finish, and we'll talk about that in a few minutes. So, one of the great myths, I call it additive manufacturing's dirty little secret, post-processing. Most people buy additive manufacturing systems expecting to hit print and get perfect parts coming off the end. Unfortunately, today that is far from the case. There's a lot of post-processing needing. Plastic parts and metal parts. Whether it's surface finish to make them nice and smooth, whether it's painting, coloring, whether it's heat treating metal parts, hipping them, and so on. So I'll give you a few examples of that. The first one, again, this is on my keychain. This is a little 3D printed spanner we did for a conference in New Zealand. Titanium spanner, it actually works, it opens and closes. Now, what you see there shown by the yellow arrows is support material. So for metal printing, it's less for support, more for heat transfer. It's to get rid of the heat out of the part so it doesn't distort. Metal 3D printing is a bit like welding. If you don't clamp things down properly, everything bends like crazy. All of that has to be removed. Now, in some cases, you can do it on a CNC machine or automate the process somewhat. In a lot of cases, you can. In this case, we had student slave labor, so it wasn't too bad. We managed to get it done without too much effort. Next example is my 3D printed aluminium guitar. So this is the aluminium guitar that's out in the lobby. This is the guitar as it came off the machine, still welded to the plate. So the plate you see on the bottom, that's the build plate that's in the machine that the whole instrument is welded to. And you can see all the support material. I think I've got a close-up here. There's all the support material that makes it up. Now, all of that support material has to be removed. And in this case, the geometry is purposefully complex, so unfortunately the only way to remove that support material is by hand. My hands were literally bleeding by the end of this. I did 2 of these guitars, and just to show you some numbers, so if I may say so, pretty incredible result, looks pretty stunning, but if you look at some of the numbers, the 3D print time is actually not too bad, 9 hours to print. That's pretty reasonable. You look at the heat treatment, we've got about 33 hours of heat treatment after that. This is to get rid of the stress, because if not, you'll cut it off the plate and the whole thing will just distort and bend. That's a lot of heat treatment. The post-processing, the first one took me 4 days to remove all the support material, 4 days of sanding, filing, shot peening to get it looking really nice. The second one, I was experienced, I knew what I was doing. I've had many metal parts produced in the past, but I always received them from the supplier with everything done already. And I really wanted to experience myself the joy of post-processing. So they sent them both to me and I did myself. And the second one took me 2 days and 2 days. So that's 4 days plus the heat treatment. It's about 6 days of post-processing after the 9 hours print. Now, this is not a problem. Every manufacturing technology has post-processing. Injection molded parts, you need to remove the sprue. Now, in a first world country, you automate the tool to chop it off. I've been to China where there's 20 people sitting around a table cutting it off by hand. It's post-processing. So all processes have it. It's just a matter of being aware of it so that when you get your first metal machine, you're not disappointed. So 2 more slides before we finish off. Some trends. Prices of machines are coming down. 2 weeks ago at Formnext, 7 new manufacturers of metal machines that have just appeared. Some metal machines are under 100,000 euros, so drastically reduction in price. CAD is improving, but still a long way to go. Material prices, I think, today are still astronomically high compared to what they should be. Nylon for a 3D printed nylon powder, you're paying roughly 20 times more than you would be for injection molding nylon. And to me, that needs to change. So the suppliers need to bring the material prices down for industry to really adopt them in a big way. And I said, mass customization, it is growing. So what's missing? Why? Additive manufacturing is great. It's wonderful. What's it missing for industry all over the world to adopt it radically? Firstly, more materials. Absolutely, we have a shortage, both polymer and metal. We need more materials in a big way. Better surface finishes? Absolutely. Currently, we're certainly in the middle to right-hand side of that surface chart. We need to be probably on the left-hand side of that, and we're not there yet. It is coming. They're getting better and better every year, but we still have a way to go. Qualifications, certification. If you're going to put a part on an airplane, you need to be able to guarantee the quality of that part. And the same for all other industries. How do you do that when it's a new process? It is being done, but a lot more work. We need better design tools. So topology optimization needs to be integrated into the CAD. And we know that Siemens NX, one of the big CAD packages, they're now bringing it. The next version will have it brought in. I believe Dassault are talking about it for SolidWorks and CATIA, so are PTC with Creo, talking about now integrating some of these tools. But they're not there yet. Engineering programs need to be very quickly updated to include design for additive manufacturing. Or how do you design? As an engineer, as a designer, you've got to really change your outlook on how you do things to really maximize the benefit that additive manufacturing can give you. So, final slide. Everything I've talked about is direct part production, making the part directly on the 3D printer. One thing that we tend to not talk about enough, and I think for industry is the biggest area, is tooling. So make things the traditional way. Keep injection molding, keep die casting, keep sheet metal, but make the tools for it using additive manufacturing. So instead of taking 3 months to 6 months to make the tool, you can make the tool in 2 to 3 days or a week. So that's another way. And there is a talk on that this afternoon. So that'll be a very, very interesting place to watch. So with that, I think we're